When we're figuring out the shape of bonds, at least the way that I teach it, you first got to be able to figure out something about the shape of the electrons around the nucleus in the first place, okay? So let's do something like, let's start with something like methane, okay? Methane's pretty simple and straightforward. And methane, the meth prefix means there's one carbon. Ane implies that there's only single bonds, but with only one carbon, there can't be any bonds between one carbon and the next. So the suffix actually goes to, or talks about the number of bonds between carbons, not between carbon and hydrogen or something else. So this is kind of, that suffix is almost useless, but it's how we write it, okay? So methane. So carbon has 1, 2, 3, 4 valence electrons, and it wants 8. That's called the octet rule. Most atoms want to have, or we think about it wanting to have 8 valence electrons. Hydrogens just have 1 electron, and they want to have only 2. It only has an s sublevel, so it doesn't need, or can't handle 8 electrons. It only wants to have 2 electrons, and so we share electrons in a configuration like this, or we show the sharing of electrons using these electron dot formulas in this manner. And so we end up with a pair of electrons squeezed between the carbon and the hydrogen like this to get a Lewis dot formula. Okay? All right. Now, carbon, the atom, before it bonds with anything else, has electrons in orbitals. That's where there's actually a shape for these orbitals. So carbon is located right here, and the 2 electrons in the first primary energy level represented by the position of hydrogen and helium here and here. Helium really belongs over here. We're talking about S, P, D, and F sublevel regions. Then you've got 2 electrons for lithium and beryllium, and then 2 electrons in the D sublevel for boron and carbon. So here's the, we could represent, we don't have to represent this way. Let's represent the first primary energy level like a sphere. So those first 2 electrons are there. And then we're going to have 2 electrons in the second primary energy level in what's called the S sublevel region. So this is the 1s sublevel region. This is the 2s sublevel region. And let's see here. I'm looking for, let's do it with this. And then inside this 2s, we're going to have p sublevel region. So here's one orbital in the p sublevel region. So we could say that's 2px. And those 2 single balloon shapes are the same orbital. Okay? And so we've got another one that goes like this. 2px. And we could say this is 2py. And then we got a bit of a problem, because the next orbital has to come out toward you and back behind everything. This is in 3 dimensions, and we only have the ability to write or draw in 2. And so we have to write something, write in a kind of, what's the word I'm looking for? Perspective. Okay, if I were in an art class, we'd call it perspective. So I have to have an orbital that's coming out toward you like this, and one that's tucked in here behind everything. Okay, and so this would be 2pz. And that starts to get kind of complex, right? But that's the way they arrange themselves. Now, we don't really need to worry about this 1s, this orange sublevel region down in here, because it's not in the valence level. And really only the valence electrons are involved in bonding. So what we really need are just the spherical region up here called 2s, and these 2p orbitals. There's one here and one here and one here. Okay? Now those can't bond in that configuration. They have to change their shape. That's called hybridization. So this spherical region called 2s, this double balloon region here called 2px, this double balloon region called 2py, this double balloon region called 2pz, they're going to change shape. So they're going to do what's called hybridization. So this 2s is going to form, instead of a spherical shape, it's going to form a single balloon shape. Not a double balloon shape, a single balloon shape. And this 2px is going to change from a double balloon to a single balloon shape. Okay? We're hybridizing. Okay? We're changing it from the original S and P to something that's neither S nor P, something in between. Like a combination between a horse and a donkey is a mule. It's somewhere in between. All right? Like a liger? Okay, sure. Now, I know what a liger, I know. Okay, so one of these two, we've got two more orbitals to deal with. Okay, we've got one that needs to come out toward you like this, and one that needs to go back behind here in order to make a sort of tetrahedral shape. Okay? And these are hybrid orbitals in the second primary level.
So is the one going behind, it's not, it's separate, right?
Yeah, they're all four separate. Okay, so this is a tetrahedral shape for these hybrid orbitals. Okay? Now then, these orbitals all have one electron in them. These single electrons we started out over here. Okay? This original 2s orbital here had two electrons in it. We need to separate those electrons out so we can bond singly to each hydrogen. And that's why the hybridization, part of the reason the hydrogen, this shaping, the reshaping of the orbitals has to take place. Okay? All right. By doing that, by rearranging the bonds, the atom is able to bond to four things. So carbon now can, by reshaping its orbitals in the valence level, can now bond to four things like I'm showing it here. Okay? The result then is that carbon is going to share a single electron it has in this orbital with a hydrogen in this direction. We're going to start out by putting the pairs of electrons. Okay? And so we get a tetrahedral arrangement of electron pairs. Okay, we change that to the molecular shape by just tacking on with the hydrogens that are actually shared with those electrons. And we get a tetrahedral molecular shape that corresponds to this reshaping of bonds, this hybridization. Okay?
Draw that bottom one like a little triangle.
This one? This bottom was coming out toward you, like this purple balloon shape is actually coming out toward you. That green one's going back behind, so this dotted line's going back behind. Okay? So
there's no specific reason why like those are like straight lines and that one's a triangle?
It's just a
yeah, because in order to have a tetrahedral where we have four sets of electrons equally spaced around this central atom, they have to push apart from each other. And they want to push apart from each other so they get as far apart as they can from each other and still be attached to that carbon. It's called VSEPR, V-S-E-P-R, for valence shell, and these spherical regions are called shells here. Valence shell electron pair repulsion. So pairs of electrons, remember, cannot get next to each other unless they have opposite spins. So we can get pairs of electrons in the same orbital, but only if they spin in opposite directions, which was what that orbital notation represented here, where we had opposite spins. They can be in the same orbital, but only if they have opposite spins. Okay? All right. We're getting there. We're almost there now, as far as the shape of the bonds. So this is showing the angle of those bonds, but it's not showing the shape of the bonds. The shape of a bond that has just two electrons in it is called a single bond. Single bonds have 2 electrons in them. The shape of that bond is sort of the shape of a hot dog, a wiener rather, not the hot dog itself, but the wiener. Okay? So the bond between the carbon and the hydrogen is in the shape of a wiener. Okay? So this would also be in that wiener shape. Now this purple one is in a wiener shape, but it's got to come out toward you. So as far as showing it, I need to have a hydrogen that's out in front, so it looks a little bigger, closer. Okay? And I'm going to draw this one so it kind of does this, coming out toward you like that. And then this hydrogen needs to be back behind somewhere, and so it's smaller. And so I'm going to show it going back there like that, so I'm going to do it something like this. Okay? So that's the actual shape of the bonds. In each of these bonds are 2 electrons. So what we've done is we've hybridized the orbitals to make this shape, and when the electron that's here shares with this hydrogen, we combine the orbital that hydrogen has with the orbital from the carbon, and it elongates a shape. This bond is a shared orbital. This bond is a shared orbital. The orbital is shared between hydrogen and carbon. So a covalent bond with sharing electrons is not just a bond, it's also sharing an orbital. Okay? Now that's the shape of a single bond.
That's the ones that we did on our models that were just like.
Sure, we did them on models.
Yeah.
Yeah. Yep. Yep. Now this doesn't show double or triple bonds. You want me to show you double and triple bonds?
No, I think it's
You got that? Okay.
Go ahead over it.
we ain't got single bonds.
Well, how we got doubles and triples? Like you can't do a single back for it, but I can do a double and a triple back for
No,
it.
because I mean I kind of get a drill on a box.
Okay. Let's talk about hybridization here with orbital notation that relates to all this, okay? We said that these kinds of orbitals cannot bond 4 times like this can. So the reason that that carbon does this hybridization is in order to bond 4 times is because that's what it needs, it's what it wants, it's what it's, well, I'm personifying it, and they're not really, you know, they're not really conscious or anything, but we're making it sound like that. The original orbital notation for carbon, we have had 1s, 2s,
This is for carbon.
this is for carbon, and 2p. Okay? So, in the orbital notation showing how electrons are arranged around the nucleus of a carbon, there's only 2 electrons that actually can share other electrons in an orbital. So in this unhybridized form, carbon can only bond twice. But we know it bonds 4 times, and that's why it does this. It does this hybridization. So let's show what happens when this hybridizes in a way that allows us to bond 4 times. Right now we've got slots in 2 orbitals for bonding. So as in this form, carbon can only bond twice. But we know it bonds 4 times. And this is the theory behind that. So we're going to take and reshape these valence level orbitals. Okay, the 1s orbital isn't going to change. It's going to stay the same. But we're going to take 2s and 2p and change this arrangement to reflect the fact that there are 4 orbitals now in this hybridized form that are exactly the same. They're not an S like this and 3 P's like these 3 P's here. There's 4 things that are exactly the same. And they're neither S nor P, but something in between. Okay? And so what we're going to have are 4 orbitals that are the same size, shape, and energy. They're in the second primary level. And these orbitals are not going to be called S, and they're not going to be called P. But since they're in between one s orbital and three p orbitals, we call it 2sp3. Now, there are 4 electrons here. We're going to put 4 electrons up here using that school bus rule, 1, 2, 3, 4. And there's the orbital notation for sp3 hybridization for carbon, where I have slots available to share 4 electrons. And you can get this methane molecule, for example. Okay?
How do we know when to hybridize?
If you're going to do covalent bonding, hybridization has to take place. So if there's covalent bonding, there's hybridization. Done. Okay? Got that? All right. But this is the configuration that carbon goes through, or the hybridization carbon goes through from this to do all single bonds. If it wants to double bond, it's got to hybridize in a different way. Okay? So let's look at, how about we look at this, H2CO, which is formaldehyde. And so for that, then, we're going to have, without going through all the, how we get to that, let's just put it into electron dot form here, or Lewis dot form. So there's a double bond. Okay? We have two sets of electrons, 4 electrons all together, shared between carbon and oxygen. Okay? Now, in this hybridization here, all the electrons are in a region directly between the 2 nuclei. We can only get 2 electrons in the same region because they have to have opposite spins. So when we do a double bond like this, we've got to have a bond that has 2 regions separated from each other. All right, for 4 electrons, I've got to have 2 different regions for electrons to sit in. And so for that, what we're going to do is we leave one of these p orbitals unhybridized. Instead of hybridizing all 3 p orbitals, we're going to hybridize 2 of them and leave one unhybridized. This is what it might look like if we're going to represent it in this form. Here's the unhybridized form, 1s, 2s, 2p, and 2 electrons in 2p. And so to hybridize it in a way that's going to allow me to make a double bond, I'm going to hybridize these 3 orbitals here and leave this 2p orbital unhybridized. So 1s is not involved in hybridization because it's not involved in the covalent bonding. But this 2s here and this 2p and this 2p are going to hybridize. So they're all the same. And then this p orbital is going to be left alone. It's not going to hybridize. Here is 2p. So these 3 orbitals here are going to be called 2sp2 because I hybridized 2p orbitals and 1s orbital. So we have 1s and 2p's here. But we're going to put the electrons in all 4 of these in that school bus rule, 1, 2, 3, and 4. Okay? Now then,
Well, where did one of those come from?
I'm going to show you that. So here's carbon. And we have 3 hybridized orbitals. And those 3 hybridized orbitals look like these single balloons up here. Okay? So I'm going to have, make sure I do this right now. Okay. Got one going here. And one coming out toward you. One going back behind. And then lastly, we're going to have one orbital that's going out like this. There's our 4 orbitals. Okay? That's what we would have had, actually that's what we had before. If I want to do a double bond, I need one of these orbitals that's not hybridized. So we got a p orbital that's not going to be hybridized. So instead of hybridizing this into a single balloon shape, I need to hybridize it into a double balloon shape like the original unhybridized form. Okay? So here's the carbon. And let's make this purple one the double balloon shape. We're going to leave it unhybridized. This is the unhybridized double balloon shape. Okay? So I've got a p orbital, a hybridized orbital that's going to be coming out toward you here. One that's going back behind. And then this orbital is coming out like this. Okay? So this is a p orbital that's not been hybridized. Okay? These three right here are the three hybridized orbitals that I have written right down here. So here's the unhybridized p orbital that corresponds to this purple double balloon shape, and these three hybridized orbitals are represented by this orange and green and pink one. Okay? Now then, we're going to need another carbon. We're going to need an oxygen. Here's the oxygen. And the oxygen is going to have this same configuration. Okay? So we're going to have this orbital coming out like this from the oxygen. Kind of an orbital that's swinging sort of out toward you at a bit of an angle. One that's going back behind here. And then a p orbital we're not going to hybridize that looks like this. So this is the unhybridized p orbital. Okay? All right. In our sp3 hybrids, the carbon's hybridized orbital reached out and sort of joined up with the hydrogens, and we made a single orbital shared between two atoms. We call it a covalent bond. Well, this is the same thing. The same thing is going to happen between the carbon and the oxygen. These are going to sort of join together into a single hot dog sort of shape. Okay? So it's hybridized into that. That makes sense?
So on the oxygen, on the top and the bottom, orbitals are they the same?
Those are two p orbitals that did not hybridize. Okay? Now, the double bond comes in because this p orbital here, which is in two parts, is going to reach out to the two parts of this p orbital. Okay? And they're going to join together. That's how we're going to get a double bond to form. So p orbitals that are not hybridized are joining together excuse me, in two parts. It's one p orbital, but it's in two parts. Like a hot dog bun has two parts, right? Okay? And this p orbital that overlaps to form a single p orbital between the carbon and the oxygen, that's called a pi bond. The bond that's in between here, that's a single bond, and we use the Greek letter sigma to represent that kind of bond. So anytime you have to have more than one bond, you've got to have a p orbital that's not hybridized to make that happen. Okay? If I wanted a triple bond, I'd have to have another p orbital that runs front and back, in front of and behind all this.